Let us solve some numerical examples. Let us say we are given a line charge which is lying along z-axis, and this line charge is finite in length. We have solved a question where this line charge was of infinite length, and we could easily use Gauss law for finding the field. But here now we are given a line charge which is of finite length. So we cannot use here Gauss law because there is no symmetry. Because of this line charge being finite in length, there will be end effects, and we cannot use that cylindrical symmetry which we utilized while solving the concept of line charge and its field when the line charge was infinite in length. So how to do it? As I have told, since there is no symmetry, we cannot use Gauss law. So we will first calculate the potential, and then we will be able to calculate the field. So let us say we want to calculate the field along the z-axis. Let us say this is point P where we want to calculate the field. So what we will do, we will calculate the potential at this point. Let us say this point is at 0, 0, z, and this is 0, 0 minus L by 2, and this point is 0, 0, L by 2. Now since we need to differentiate between the source point as well as the observation point, so what I will use prime coordinates for the source points and unprimed coordinates for the observation or field points, so that we are not confused with that notation. Let us take a small charge of length dz dash. Okay, and this length this dz dash line charge will have a charge of dq will be given by lambda dz dash, where lambda is the line charge density. Now let us say this this element is lying at the coordinate given by 0, 0, z prime. Okay, so this is lying at 0, 0, z prime. Now we want to calculate the electric potential at this point P. It will be simply V at P will be given by, or dVp, because we are just calculating because of this differential charge, lambda dz dash 4 pi epsilon naught, and the distance between the source and the observation point. So distance between source and observation point is z minus z prime. So the potential because of the full line charge will be integration of this dVp. Vp is equal to this is equal to lambda will be a constant, 4 pi epsilon will be a constant, so it will come out of integration dz dash z minus z dash, and this z dash is going to vary from minus of L by 2 to L by 2. So on solving, it is simple integral only, which will comprise of logarithms only. So I will get lambda by 4 pi epsilon naught natural log of z plus L by 2 over z minus L by 2 for z being greater than L by 2. Means the point should be above the line charge where we are going to calculate the potential. So we have got the expression for the potential at point P, which is above the line charge. Now we can calculate the field at this point. It is simply, now since you can see this potential is just a function of z only, so we can hope that field will be simply in z direction. So we will put the value of Vp and we will differentiate with respect to z. What I will get? We will get Az. Of course, we know the direction will be in z direction only. Lambda L, the length of the line charge, over 4 pi epsilon naught z square minus L by 2 whole square. So this will be the field due to this finite length line charge. So you see, in this scenario we could not use Gauss law, so we have utilized the concept of potential and calculating electric field from that. Now, in the next example, which we will solve in the next slide, we will solve a numerical example which is very conceptual in nature, and it has been asked in GATE also in some previous years. Now let's see this example. Here we are given a conducting shell with inner radius Ri and outer radius Rho, and we are told that there is a point charge at the center of this conducting shell with magnitude Q. We need to find the field as well as potential at various locations. So first we will start when we are outside the shell. So since there is spherical symmetry, we can make a Gaussian spherical surface which is going to enclose this whole shell, and from that we can easily find that E dot ds is simply E 4 pi r square is equal to the charge enclosed. So E is simply Q by 4 pi epsilon naught r square when r is greater than r naught, and the direction is simply the radial direction. So this is the first part. Now we need to find the potential at this point. So potential V1, let us say we will call it as V1, is simply minus infinity to this. Let us say we want to calculate the potential at this Gaussian surface. So this is R. So we want to calculate the potential at this Gaussian surface. It is simply minus E dot dl from infinity to r. Now dl will be simply in direction of radial direction because the field is in radial direction only. So we will get simply minus q by 4 pi epsilon naught r square dr from infinity to r. So v1 will be simply q by 4 pi epsilon naught r, assuming that at infinity the potential is 0. So this is for r is greater than r naught. Now in the next slide we will calculate what happens when we have the point within the shell. So let us say this is the scenario now. We have this shell with concentric shell, of course, Ri, r naught, and now let us say we want to calculate field and potential inside this shell, within this meat of the shell. So let us say this is r. So what is the scenario? R naught is greater than R is greater than Ri. This is the scenario. So again, due to spherical symmetry, the field will be in radial direction. Of course, since this is a conducting shell and we are in the meat of the conductor, so the field will be actually 0. Okay. So potential at this Gaussian surface will simply be V2, let us say, is simply minus infinity to Rho E dot dr minus Rho to R E dot dr. Now this is 0, so this part is 0, so it is simply Q by 4 pi epsilon naught R naught. So the potential in the meat of this conductor is 1 Q by 4 pi epsilon naught R naught, which is a constant since it is an equipotential. Now let us say we want to find out the scenario what happens inside this shell, the inner surface. So what is the scenario now? This is the shell. We want to calculate at some point which is inside the shell. So what is the scenario? R is smaller than Ri. So field will be Simply E is equal to Q by 4 pi epsilon naught R square in radial direction. We can easily calculate using Gauss law. But how to calculate the potential? It can easily be calculated now. We can see, we can come from infinity to this point. So first we will come to R naught, then R naught to Ri, then I will take minus sign everywhere. Then Ri to this R. So V3 is simply minus of Q by 4 pi epsilon naught R square dr this infinity to R naught. Now this portion will be 0 because inside this shell from R naught to Ri field is 0. So I will not write this, and from this Q by 4 pi epsilon naught R square dr from Ri to R, we will now integrate this. So this V3 will be Q by 4 pi epsilon naught 1 by R naught plus, it will be 1 by R naught plus 1 by, from the second integral, 1 by R minus 1 by Ri. So this will be the potential inside the shell. So now let us try to plot these. First we will try to plot the field. This is radial direction, and let us say this is the magnitude of the field in the radial direction. So it will fall with the square up to R naught. This is R naught, and from R naught to Ri it will be 0, and then it will again rise to Q by 4 pi epsilon naught Ri squared, and it will fall down with the square. Okay, and this is Q by 4 pi epsilon naught R square. This point is Q by 4 pi epsilon naught Ri square. So this is the scenario which we will face. Of course, I actually made it little uh, uh, reverse, in reverse sense, because field will start from the charge. So this is the 0, this is Ri, sorry, and this is R naught. So this will be R naught squared, and it will gradually fall to 0 at infinity. So in this way we can plot this field plot. So you see that field is not continuous. There is this jump discontinuity at these 2 points. Now let's plot the potential. Let us plot this potential. This is potential axis, and this is R axis. This is V, and let us say we start from 0. We will meet at Ri, we will meet at Ro, and this is infinity. So the potential will start from infinity and it will reach to the point V3. It will stay up to that value, uh, which is Q by 4 pi epsilon naught R naught, not V3. I think it was V2 in our expression. And then it will decay again with Q by 4 pi epsilon naught R. So in this way you can see that this potential is continuous at all these 2 points. The potential is continuous, but the field is having jump discontinuity. So you see, any jump discontinuity in the potential will mean that the field is infinite. So that cannot be possible unless we have a charge there. So in this way, you can see that potential is going to be continuous, not the field. So I think this is one of the question which was asked in some previous year gate, and many of the students were confused. So now I hope that your doubt is resolved. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel, and also join the Telegram channel, whose link is given in the description of this video. Thank you.